I'm going to start reviewing and giving some review notes on Unit 1. I'm going to cover probably a little more than half of this topic. I'm going to go quickly, but you can certainly pause and go back over areas that you need to work on. The beginning of this unit is pretty basic. I'm not even going to put up the notes that you would need on moles and molar mass and basic converting Avogadro's number. There's no real stoichiometry in this unit yet, just pretty much molar mass, grams to moles, moles to grams. After that, it gets into empirical and molecular formulas, percent composition or percent by mass. So if you know the percent of each element, you can come up with a formula for that simply by turning your percent to grams to moles and getting your mole ratios as whole numbers. Your combustion analysis is a high-level thinking process of that same skill. So if you can do a combustion analysis, you should be able to do any kind of mole problem that there is. Again, for basic combustion analysis, you have, and you had one for your previous homework that we'll look at, you're looking at all of the carbon being sequestered into the CO2, all of the hydrogen into the water. So when you burn this compound, you're able to get the grams and then the percent and moles and eventually a formula for that compound. Gravimetric analysis is another use of turning things to moles. So being able to turn grams to moles and moles to grams is a skill, but what they're going to want from you is to solve a problem, come up with a formula, or analyze something. So it does take some practice in figuring out how you're going to use that basic skill to solve these problems. So gravimetric analysis is taking a sample that contains lots of different substances and breaking it down and finding only the substance that you're interested in. So we could have any kind of sample that contained the calcium ion. We would do whatever we needed to do to get that calcium ion separated from the original solution. And for almost all gravimetric, that's making a precipitate. So you might dissolve it so that you release the calcium ions. Then you would precipitate all of it. So you could be asked a lab question, and I've got several good free response for you to work on this. What do you need to do? You need to make sure that you had access to precipitate everything. You have to precipitate it to a known formula. This one happens to be a hydrate. But once you know that known formula, then after you do the wash and dry and filter and weigh, you're going to take that known compound and analyze it for your calcium ion. So it's taking and creating a known compound that you can then back analyze. The math for something like that has you turning the known precipitate into moles of that precipitate with its molar mass. And then this is the crux of everything. In 1 mole of this, you have a mole of calcium ions. If you were analyzing for carbon, you have 2 moles, or for oxygen, 4 moles, or for water. So it's based on that relationship of the part to the whole. Once you get to the part, then you know the molar mass of that species, and then you can divide it by your original sample and get your percent of that species in your unknown substance. From that basic math of grams to moles, moles to grams, empirical formula, they move into atomic structure. So atomic structure, I seriously doubt you would ever be asked, especially with this shortened exam, any historical experiments. But remember, we start off with J.J. Thomson discovering the electrode with the cathode ray tube, move to Ernest Rutherford finding the nucleus with the gold foil experiment, so that we now know there's some negative and positive charge in the atom. That is crucial to our basic understanding. The breakdown of alpha and beta and gamma particles is no longer on the exam. There's no nuclear, so we'll skip that. But it leads to isotopes, and isotopes are important, that you understand the mass number the atomic number, what these numbers mean. What you're really looking at is finding out, here's your nucleus, where are these electrons located and how do they affect the behavior. So if you remember, you go from atomic structure into bonding, into molecular structure, polarity, intermolecular forces. All of this is the beginning of that knowledge. So one of the types of spectrometry you're expected to understand is the mass spectrometer. So you will inject your sample. These are separating by the simple mass of the species. It goes through and is vaporized. It's hit with an electron beam that knocks off the electrons to give you these positive ions. They're pulled through this negative field to get them moving. They pass through this big magnet field and they are deflected based on their mass. The ones that are deflected more have a lower mass than the more massive ones. So when the computer prints out peaks, it tells you how many hits you had and what mass you have of that element. The math then is pretty simple. The percent times that mass and you get a weighted average. Your ions again are deflected by the mass and also by the charge. The lighter ions are deflected more, but ions with a greater charge, maybe a 2 positive charge, are also going to be deflected by a larger degree than those with a 1 positive. I think for what they're going to ask you, they're going to focus on that mass. So that mass charge ratio can be a factor, but this is not anything I have seen discussed on the exam, and with 45 minutes, this is not something we're going to focus on. But you do need to be able to look at a drawing that shows a deflection of species A and species B, and look at silver ion 107 mass and an isotope with a 109. And by looking at the fact that the A shows a more deflected path and that the smaller mass would be deflected more, you should be able to identify this as silver 107. When you get a mass spec data, it could be given to you very straightforward. You've got about 50% of your mass of 90 atomic mass units. So again, putting in your 0.5 times your 90 and then adding up your 91 mass times whatever percent and coming up with a reasonable average atomic mass. The other way it could be shown, and I have seen it shown, is that instead of percents, they give a relative abundance, and they assign the highest percent a 100. So if you get something like that, there's a little more math involved. It's still the same idea. So the tallest peak is given an arbitrary height. They can have all kinds of scales, but what you're looking at is the relationship of the percentages of those scales and the masses. So with something like this, you would simply look, if you have got your highest assigned 100, that gives you a total of 123. So 100 out of 123 gives you an 81%. 20 out of 23 gives you an 18%, and then you do the math the same way that you always do. Make sure you can find the average atomic mass using mass spec data. Pretty straightforward. You could be given something a little deeper in thought. If you were getting the mass spec data for a diatomic element and you have 2 isotopic forms, then you can see that you have some peaks where you have the diatomic element with 2 bromine 81s, or with 2 bromine 79s, or with a bromine 7981. So you're looking at which of those is the most common arrangement of those 2 isotopic forms.